Okay, hello everyone. Today we will learn about linear models and estimation by least square part 4. This is chapter 11.6, which is inference concerning linear functions of the model parameters. And this is for the simple linear regression. However, I'd like to cover both simple regression case and also multiple regression case, which is 11.12. So I will move. I will explain about 11.6 and also right after that I will explain about 11.12. So they are simple regression version and also matrix version for multiple regression. Okay, so let's think about the simple regression version first. Suppose we wish to estimate expected value of y, which is beta 0 plus beta 1x. So this is the simple regression version for estimating expected value of y. And suppose we wish to make an inference about theta, which is a linear combination of beta 0 and beta 1. So let's say that we are interested in theta that is a0 beta 0 plus a1 beta 1. So this is our new theta of interest. And to estimate for theta, we can define this way. Let's define theta hat as a0 beta 0 hat plus a1 beta 1 hat, and we can easily show that this is unbiased estimator, and also it will have other interesting properties. Let's move on. So this is unbiased estimator. We can easily prove that by taking expectation on theta hat, we can check that it is a0 expected value of beta 0 hat and plus a1 expected value of beta 1 hat. And since we already proved that expected value of beta 0 hat is beta 0 and expected value of beta 1 hat is beta 1, so it is theta and it is unbiased estimator. And also for variance of the estimator, it's we can easily show what it is by using the theorem that we already learned. So to calculate variance of theta hat, it is a0 square variance of beta 0 hat and plus a1 square variance of beta 1 hat and plus 2 times a0 a1 covariance of beta 0 hat and beta 1 hat. Actually, it is just the calculation, the method of calculation. So I already proved what is variance of beta 0 hat, what is variance of beta 1 hat, and what is covariance of beta 0 hat and beta 1 hat. So so you can easily prove this by putting all these together, and if you rewrite everything, then it becomes this equation. So I will skip the details, but if you are interested, please try to find this by yourself. Yeah, okay. Okay, let's move on to multivariate case, which is covered from chapter 11.12. Okay, suppose we wish to estimate EY, which is multiple regression, beta 0 plus beta 1x1 plus dot 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 beta kxk. And suppose we wish to make an inference about theta, and the theta is a linear combination of beta 0 to beta k, which is a0 beta 0 plus a1 beta 1 plus dot 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 ak beta k. And in this case, we can write it using vector. So let's define our vector a as this, a0 to ak, and let's define the beta this way, beta 0 dot 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 beta k. And then we can express this theta as this. So A transpose is a0 a1 dot 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 ak, and beta is beta 0 dot 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 beta k. The product of this calculation is that a0 beta 0 plus a1 beta 1 plus dot 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 ak beta k, which is this thing. Okay, and for the estimator for theta, we can write it this way, and we can easily prove that this is an unbiased estimator and also have other properties similar to the simple regression case. So for the unbiasedness, the proof is very similar. The expectation, since A0 to AK are constant, so expectation is on these variables. So the expected value of beta 0 hat, expected value of beta I hat is beta I. So we can easily show that the expected value of A prime beta hat is A prime beta. And also for the variance part, actually, we should know this formula. So variance of C, which is constant, and X, and let's say that this C is a vector, and so let's see as n by 1 vector, and let's define X as n by m matrix, and let's say that n by 1 n by m, yeah, n by 1 matrix, and let's say that this matrix X are random variables, and in this case variance of C prime X can be written as C prime variance of X and C. Also, I also explained that if this is matrix, so let's say this is m by n matrix, then variance of n x is n by 1. Here C transpose is 1 by n, n by 1. Okay, and for this case, this is A variance of X and A transpose. So I will admit that I will admit this property, and you will learn why this holds from probably multivariate statistics class or linear model class. Anyway, I will assume that this one holds and explain this thing. So this one, before I explain this one, we showed that variance of beta hat is X transpose X inverse sigma square. And so variance of A prime beta hat, it becomes A prime variance of beta hat A. And since we know that this is this, it is A prime X transpose X inverse, and sigma square is just constant multiplication, so we can write it this way. This sigma square is 1 by 1 constant, so we can write it in the back side. Okay, so this is the proof for this one. Okay. To test H0, which is theta equals theta 0, and theta is again the linear combination of beta, and we need assumption that epsilon follows normal distribution with mean zero variance sigma square. If we have this additional assumption, then we can also derive that our theta hat follows normal distribution. Again, this theta hat is the linear combination of betas. So A0 beta 0 hat plus A1 beta 1 hat. So this is linear combination of betas, and we know that beta 0 and beta 1 follows normal distribution. And the sum of normal distribution is also again normal distribution. The mean is theta because it is unbiased, and the variance is actually we calculated the variance of theta hat. That would be this one. You can use the formula that we learned in the previous slide to calculate this variance. And to construct the confidence interval, you can again use the similar similar formula to calculate confidence interval. And also, if the sample size is not enough, if it is small, then you can use t distribution after replacing this one with s. Okay, the standard error estimate of theta hat, actually, anyway. Okay. So to test theta equals A0 plus beta 0, A1, beta 1, for the hypothesis of this, you can use the test statistic of this one, t statistic. If n is sufficiently large, then you can use z as your test statistic with the same calculation. So if n is like less than 30, you can use t distribution to find the rejection regions. But if you have more than 30 samples, you can use z, like z alpha or something. You can use the normal distribution to do the inference. So this is for a test for theta, and you can construct construct confidence interval for theta this way. Okay. Now to test if your hypothesis is for the multiple regression case, if your hypothesis is A prime beta equals something, then you can use the test statistic of this thing, A prime beta hat minus A prime beta. Actually, what you can use is that A prime beta hat follows normal distribution with mean 0, and variance is this thing, A prime x inverse A sigma square. So you can use this distributional assumption to derive the normal distribution like this, and using this distribution, you can construct 100% 100 times 1 minus alpha percent confidence interval for theta as this way. And also, if you have not enough sample, like if you have small samples smaller than 30, you can use t distribution this way. Okay. And so the procedure is described here. For testing A prime beta for the null hypothesis of this, and if your alternative hypothesis is this, you can use the test statistic t this way, and this is rejection region, and this is the degrees of freedom that you will use, and also here's the confidence interval so the formula for confidential interval. Okay, and let's move on to example 11.15. Do the data example 11.1 present sufficient evidence to indicate curvature in the response function? Test using alpha equals 0.05 and give bounds to the attained significance level. So the first problem is do the test using alpha equals 0.05, and the second is give confidence interval bound. I use 95% confidence interval bound, and here what we need to show is evidence to indicate curvature, which means the whether we can assume our y as beta 0 plus beta 1 x plus beta 2 x squared plus epsilon. So whether we can explain the data given here using this term. So the hypothesis testing becomes this one, whether the beta 2 coefficient is 0 or not. And to do the hypothesis testing about this, we can construct we can say that our A is 0, 0, 1. Then our hypothesis testing H0 becomes A transpose beta. Here beta is beta 0, beta 1, beta 2, and so A transpose beta equals 0, which is this thing. So this implies beta 2 equals 0. So let's try to derive the distribution of A transpose beta. This follows normal distribution A transpose beta hat. This follows normal distribution with A transpose beta, and also the variance is X transpose X inverse A transpose A sigma square, and we can replace this sigma square with S square, and here we only have 5 points, so we will use T distribution. So our T distribution would be A transpose beta hat minus A transpose beta, which is 0, and divide by square root of S square, this thing S square times A transpose X inverse A. So this is our T statistic, and the degrees of freedom is n minus k, which is k is 3. We have 3 parameters to estimate. So this is 5 minus 3, which is 2. So df is 2. Okay, let's move on to calculate our test statistic. So now the data is this thing. The x data for x matrix, x is 1, x, and x square. So the data is 1, 1, 1, 1. X is given here, minus 2, minus 1, 0, 1, 2, and x square is 4, 1, 0, 1, 4. So our matrix x is given like this matrix, and y is 0, 0, 1, 1, 3 from here, and also n, there is the number of observations, which is 5, and the p is number of dimension in x, which is 3. Actually, number of parameters to estimate. The p is the number of parameter to estimate, which is beta 0, beta 1, and beta 2. So this is 3. And the a, vector a, is 0, 0, 1, which is this thing. Okay, and we can estimate beta hat like this: x transpose x inverse and x transpose y. This is beta hat. And we can estimate s square like this, and our estimated s square value is 0.2285 or something like here. Okay, and now let's try to calculate the t statistic here. Okay, so firstly we firstly calculated the variance term, this one. This is the variance of beta. A variance of beta hat is this thing, and from here the variance of A transpose beta hat is A transpose variance of beta hat A. So this is by definition so square root of variance of this thing, which is this one. And so this is the t statistic that we have. And what else? So since we calculate this t, we should calculate the decision rule, and this is this thing: qt 1 minus 0.025, and degrees of freedom is n minus 3, which is 4.30, and the derived statistic is not greater than 1.67 is less than 4.302. So we cannot reject the null hypothesis. So the conclusion is to not reject H0. So this is our conclusion. And also, we need to give the bound to attain the significance level. And before we calculate this thing, from the value, from the t value, we can calculate the p value. And to calculate p value, you can use this code to calculate p value, which is actually calculating these two things, since it is two-sided test. And also to calculate the confidential bound, you can use this formula. So here t 0.025 and times this thing is square root of the variance term, this one, square root of A transpose X inverse A and S squared. So this is the bound side, and this is the beta 2. So beta 2 plus and minus this bound will give you the confidential bound, which is minus 0.3352 0.764. Okay. And usually after we fit the model, we want to do the inference at a point. We can do the inference at a given point, and that is this thing. Expected value of y at a given point x star is beta 0 plus beta 1 x star. And actually, this one is the linear combination of beta 0 and beta 1. So in this case, we can set A0 is 1 and A1 is x star. Then for theta equals A0 beta 0 plus A1 beta 1, this is linear combination of beta 0 and beta 1. And so we can do the inference about the point, about the given point. And the variance of that point can be calculated like this, and with this knowledge we can do the inference at a given point. So for the confidential interval for the new observation, x star can be given this way. So let's try to use this formula to construct the confidence interval, 90% confidence interval for expected value of y when x equals 1. And to do this, from the previous table, we can calculate beta 1 and beta 0 from the formula like this. So beta 0 estimate, so our beta 0 estimate and beta 1 estimate for these case is 1 and 0.7, and here our new observation x star is 1. So here x star, we define x star is 1, new observation is 1, and we can calculate the sum of square error and s square like this. And what else? And we can calculate this value. This is square of this value. So T alpha over 2, which is 1 minus 0.05, we are finding 90% confidence interval. So alpha is 0.1, alpha is 0.1, so alpha over 2 is 0.05, and so this one times, so this is T alpha over 2, and this is S, and square root of this thing, this is square root of 1 over n plus x star minus x bar squared over sxx. and so the result is 0.78. And also this value is 1.7. So the confidential interval is 1.7 plus minus 0.785. 0.785. So this is 90% confidence interval from the formula. Okay. Now let's again solve the same problem using the way that we learned from 11.12. So in this case, vector A can be defined as 1 and 1. And so let's see. So A transpose beta is beta 0 plus beta 1, which is beta 0 plus beta 1 x star. Okay, so what would be the distribution of A transpose beta hat? It will follow normal distribution with A transpose beta, and the variance component is A transpose X transpose X inverse A sigma square. Actually, we will replace this sigma square with S square, and also the distribution should be I used notation normal, so with this is sigma square. And we were going to use T distribution, which is A transpose beta hat minus A transpose beta divided by square root of S square A transpose X inverse A. We'll follow T distribution with degrees of freedom n minus 2. Because we are estimating beta 0 and beta 2, so number of parameter is to estimate is 2. And so what else? Now it is time to calculate. Oh, actually, the confidential bound can be calculated t alpha over 2 with degrees of freedom n minus 2 times this thing, square root of S square A transpose X prime X inverse A. So this is plus minus A prime beta hat, which is beta 0 plus beta 1 X star, which is beta 0 plus beta 1. Okay. Now let's try to solve using R. So our X matrix is this thing. Our X matrix is again 1 1 1 1 and minus 2 1 0 1 2. This is our X matrix, and Y matrix is this thing. The N is the number of observation, P is number of parameters, beta 0 and beta 2, and A is 1 and 1. Beta head can be estimated by this, and S square can be estimated by this formula, and variance of beta part can be estimated like this, and this is variance of beta, and we can calculate the T distribution. This thing we can calculate it like this. This is A transpose beta hat divided by square root of A transpose of variance of beta hat A, and here variance of beta hat is X transpose X inverse S square. And since S square is constant, it can be go like this way, and A transpose X. Okay, so you can check that this is exactly same as this thing, and also you can calculate this A prime beta hat, which is this thing, and it is 1.7. So it is 1.7 plus minus, and the term here, it is this part is T alpha over 2 with degrees of freedom n minus 2, and times this part is again this part, square root of A transpose variance of beta hat A, which is actually same as this one, and then it is 0.7805, it is 0.7805, and this is same as the one that we calculated in the previous example. Okay, here is homework for chapter 11.6 and 11.12. Okay, this is end of the lecture for this week, and let's see you next week. Thank you.